Query evaluation efficiency can be improved using pipelining. Using pipelining, the result of one operator is pipelined to the next without creating a temporary table. In this way, the writing of the temporary tables to the disk and reading them back again for the next operation is eliminated, providing a potentially significant cost reduction. Using the same example we saw in materialization, say we are given the expression to apply projection with attribute name on the result of selection with building name specified on the department relation, joined with instructor relation. Using pipelining, we will not store the result of selection in a temporary table. Instead, we provide it directly to the join. The same applies to the result of join and providing it to projection. Not needing to store a temporary relation to disk causes the cost of evaluating an expression to be lower. However, it comes with a caveat that this, as opposed to materialized evaluation, may not always be possible. For example, pipelining might not be possible for sort or hash join. Pipelining, in simple words, is implemented by combining the intermediate operations and constructing a single complex operation that includes the pipeline. Whenever possible in the process, we have a choice in implementation of pipelining. We can either take a demand-driven or producer-driven approach. In the demand-driven approach, each time an operation receives a request from the system for tuples to be returned, it computes them and returns them. This approach is therefore called lazy evaluation or the pull approach. The interface for this approach could be implemented using open, next, and close functions. After a call to open, each call to next returns the next output tuple of the operation. The operation, in turn, calls open and next to its inputs. The function close tells an iterator to stop as no more tuples are required. The producer-driven, eager, or push approach instead uses a separate thread within the system that takes the stream of pipelined inputs and generates the stream of its outputs. It does not wait for the system to ask for each tuple. What we discussed in query evaluation was based on determining I/O cost. This is because our focus in this course is on disk-oriented relational database management systems. Therefore, the I/O cost is the big portion of the total cost of operations. However, the cost of evaluation of queries in memory, although not as high as I/O, can also be optimized. This can also help in performing more of the work in memory. In processing the queries in memory, the CPU cost becomes a bottleneck. One of the ways to reduce this cost is replacing the interpreter with a compiler. In executing the query plan, traditional database query processors act as interpreters. This could introduce huge overhead. For example, repeated attempts for finding attribute location within tuple from the metadata could cause overhead. Modern main memory databases alleviate this with query compilation that translates query plans into machine code or an intermediate level bytecode. This has shown to improve the processing performance by up to a factor of 10. Usage of column-oriented storage, that we will briefly discuss in advanced topics, can also have benefits in operations involving few columns of huge relations. So, keep this in mind till then. Cache-conscious algorithms can also help in improving the in-memory processing. The goal of cache-conscious algorithms is to minimize cache misses. This could be achieved in different ways by best use of data fetched into the cache. For example, by laying out attributes of tuples that are often accessed together in a way that they are stored adjacent to each other.